So today you'll notice that we're adding in a couple more transformations beyond what we did yesterday, because yesterday was all just shifting our reciprocal functions. Today we're adding on a couple. So in this particular equation, as we take a look at it, we actually have two transformations that we're adding in on this. The first one comes from the negative that's out front. If you have a negative out front, what does that do to our graph? How do we describe that? And so yes, it is a flip or a reflection, but the key is that we see that it's actually across the x-axis. It flips upside down. And so this is going to start as a reflection across the x-axis. So up is going to become down, down is going to become up. And then we also have the 2 here. Now that 2, writing something like 2 over x, is the same as actually having started as 2 times 1 over x, which might help us to see what that transformation is. You might also know from the notes we took yesterday, what is that 2 going to be doing as a transformation? It is a vertical stretch by a factor of 2. So multiplying by 2 is a vertical stretch by a factor of 2. And as you may recall from the work we did back with sine and cosine, we really do need to be specific about whether it's a horizontal or a vertical stretch, because they will give different feels depending on what kind of graph we're doing. In this graph, it'll happen to be very similar, but we've seen that it can make a huge difference. All right, so now that we know our transformations, the very first thing I do when graphing a reciprocal function is I draw the asymptotes on. And as you may recall from yesterday's work, our asymptotes normally live at 0. Both horizontal and vertical. Well, in this case, is the negative, that is our reflection across the x-axis, is that going to change where either of those asymptotes are? No. Because like if I take this vertical one and flip it upside down, it's still a vertical line in the same place. And the horizontal one, if I flip it upside down, it's at 0, and 0 reflects to still be at 0. So that doesn't change it at all. What about the vertical stretch by a factor of 2? Does that change either of those asymptotes? No, because again, 0 times 2 is still 0. So my asymptotes haven't moved with this. So based on that, we can see that the only thing that will change the asymptotes is the shifts that we were doing yesterday. Those are the only things. All right. Now that we've drawn in our asymptotes, time to start plotting some points. Now, if I was just going to be graphing the parent function, 1 over x, where would I put my first point? Yep, 1, 1. Over 1, up 1. So it would normally be here, although in this case you can bet it's not going to be, right? So we got to apply 2 transformations to that point. The first thing we need to do is reflect it across the x-axis. So I'm going to take that point and it flips upside down. So that would mean instead of going up 1, we're going down 1. But, of course, all that did was this part. We still have the vertical stretch by a factor of 2, which means that instead of going down 1, we're going to be going down twice as far. And so instead of down 1, we go down 2. And since I've now used both my transformations, that is where that point ends up. So we can go ahead and plot that. So notice, basically, all we got to say is that up 1 becomes down 2. We can actually get all of the rest of the points by similar reasoning. But we actually do need to think them through point by point. So, for instance, normally I would go over 2 and up, how far? How far up do we normally go if I go over 2? A half, yeah. Because it's 1 over 2, because the parent function is 1 over x. So that's normally up a half. Notice 2 and 1/2 are reciprocals of each other. This is called the reciprocal function. Notice the connection there. All we got to do is reciprocal to know how far over and up. All right, so if I would normally go over 2 up 1/2, in this case, I'm going to go over 2 and down how far? 1. Because I'm doing the 1/2 that I normally go up, and I'm multiplying it by the 2. 1/2 times 2 is 1, hence why it's down 1. Now, I know based on the work we did back with exponentials, Some of you are thinking right now, oh, this is super easy because all I have to do is just keep cutting the height in half. That's true with exponentials, but not with this one. And let's actually see why that is here. If I go over 3, how far up should I be going normally in our parent function? 1/3. Well, what is 1/3 times 2? 2/3. So instead of going up 1/3, I'm going to be going down 2/3. And yes, we're estimating where 2/3 is. You know, we can't be perfect when plotting 2/3, but we can be pretty close. So we plot the 2/3 there. So notice I didn't just take the 1/2 and cut it in half again. I actually had to think normally it's 1/3 and then multiply that by 2. And we can keep going along the same line. So like for instance, over 4 is normally up 1/4. If I double 1/4, I get 1/2. And so I'd be going down 1/2 there. And I could do that for any of those points. When plotting these, just like the stuff we were doing yesterday, I want you to plot the first point, the one that's normally over 1, up 1, put that wherever it ends up in this case, and then give me at least 2 of the points on that side of it. Now that we're doing the stretches, having 2 points rather than just 1 point on that side is going to be a big help, because it's actually very easy to just plot one of those points and have your graph come out looking a little bit wonky because of the stretch being in there. All right? Now, the same way that we have to plot 2 points on that side, we're also going to have to be plotting 2 of the points on this side of it. And so we need to now take a look and see what is happening over here. Well, let's go ahead and take a look at that. Normally, I'd be going over 1/2 and up. What's the reciprocal of 1/2? 2. So normally it's over 1/2 and up 2. That's where I'm normally going. So in this case, remember it's a vertical stretch, so I still go over 1/2. It doesn't affect the horizontal at all, but it does affect the vertical. So instead of going up 2, I'm going to be going down 4. I'm going down twice as far as I normally would have gone. And of course, we need another point over there. So let's go over to 1/3. Just because it's nice and easy to do the reciprocal of that. Technically, you could use anything. But if I go over 1/3, the reciprocal of 1/3 is 3. So normally it's over 1/3 and 3. In this case, then, that would be over 1/3 and down how far? 6. And so that would then give me that point. But of course, it doesn't have to be that one in particular. You might have said 1/4 and 8. Or you might have said 1/5 and 10. Because I'm always just taking the reciprocal of it. So like the reciprocal of 1/5 is 5. And then I'm multiplying that height by 2. All right. Now, remember this is only half of our graph. And sometimes I see people wanting to stop at this point. We don't want to stop there. So, I now need to know what is happening up here. And I need to start plotting some points up here in order to be able to know that. Well, there's 2 ways you can go about it. One way is you can say, well, normally I'd be going left 1, down 1 to get to that point. I'm going to flip that upside down, and then I'm going to double that height, and so I'm going to be going left 1, up 2. That's one way you could get that. The other way is using the symmetries of this graph. So let me illustrate here. This point right here, the very first point that we plotted on that side, was right 1, down 2. Notice this point up here, it is left 1, up 2. See the connection between that and the other point that we plotted? I'm just reversing the direction of both of those, but the amount is the same. So we went over 1, and we went vertically 2. Same thing. It's just we swap whether we're going left and right and whether we're going up and down. And the beautiful thing about that is it actually makes it easier now to find out some of these other points. So for instance, like if I know that for this point, to get there, I'm going right 2, down 1. Well, if I flip that around, that means I would have to be going left 2, up 1. So I must have a point there. And we can do that for all of those points. I can take whichever points that I chose to plot. Remember, 2 on each side. And I can just swap the directions that I'm going in. But I'm still going the same amount. I'm still going over and up by the same amounts. It's just I'm switching whether I'm going up and down and whether I'm going left or right. And of course, once you've drawn in those points, then you can go ahead and draw your curve through it. Now, as we move on to our second and last graph of the day, it's all about the equation and being able to read the equation correctly. And this particular one can cause us some trouble. So I really want to make sure to emphasize the format of the way this was chosen to be written and get you to see how to handle it. Otherwise, it's going to throw you off. Because normally, we see a number that's added or subtracted on the end here after the fraction. And all of a sudden, we have something written in front of it instead. And that can easily throw us off if we don't take our time and really think through it. So we're going to start by just figuring out what this 4 does. You'll notice that once we figure out the 4 and why it does what it does, everything else is going to be a lot easier to do. Because the 4, is the 4 itself positive or negative? It's positive. And so because of that, notice the fraction. Is the fraction positive or negative? It's negative. Which means that if I wanted to rewrite this into a more comfortable form, that means this is exactly the same as writing it like this. Negative 3 over x plus 6 plus 4. That's the exact same thing. And so since the 4 is positive and it's being added in, which way is it moving it? Up. And you notice I know it's moving it because every time you add or subtract, it is always a shift. Multiplying is a stretch. And so knowing that these two equations are exactly the same and mean the exact same thing is going to save you a lot of trouble. Because a lot of people get confused up here and they actually end up trying to like shift it down 4 or something like that instead. And it throws everything off. So you have to see it there the same. All right, so transformation-wise, we already talked about the 4. We know that is going to be up 4. Let's go ahead and just keep going through it then. Next step, the negative that's sitting out front of it. What does the negative do to our graph there? Yep, as we saw in our last example, that would be a reflection specifically across the x-axis. Next up then is the 3. Well, this is kind of like the 2 that we saw, right? The 3 is a vertical stretch by a factor of 3. And finally then that leaves us with the plus 6. What does the plus 6 do? Yep, that's going to go left 6. And so make sure you have that list of transformations correctly written down for this equation. So when we now go to graph it, the very first thing we need to do then is think about where am I going to draw my asymptotes. The asymptotes, remember, are changed by the shifts, and only the shifts. So the reflection in the stretch will not affect the asymptotes at all. Because of that, I know I'm going to have an asymptote that is left 6, and I'm going to have an asymptote that is up 4. So I start by drawing those in. Both as dotted lines, please, not solid. And those are going to be our guides as we go and draw this. And the great thing about drawing in those asymptotes first is effectively we've just dealt with these two shifts and I no longer even need to think about them. Really, I'm just looking at those asymptotes, ignoring the x and y axis now, and I'm just thinking about what's left in the equation. And all that's left in the equation is y equals negative 3 over x. Meaning that this graph from here is just going to look very similar to the last one that we did. It's just relative to those asymptotes now instead of the axes. And of course we got a 3 instead of a 2. So let's get the first point plotted. The first point, if I was just graphing 1 over x from here, remember the first point would normally be over 1 up 1. So instead of being over 1, up 1, it's going to be over 1 and what? Down 3. Because instead of going up, I'm going down because of the reflection there. And instead of going down 1, I'm going down 3 times as far. Hence the vertical stretch. All right, now from here, again, you get to select any 2 points you want to over here to plot. Now, a lot of you, you're just going to go to the next whole number that you can see, which would be 2. So let's say you go to 2 next. Well, if I go over 2, how far up do I normally go? 1/2. The reciprocal of 2, of course, is a half, so I normally do that. So I'm going to be going down 1/2 times 3. What is 1/2 times 3? It's 1.5, 1.5, 3 halves, any way you want to say it is fine. But that means that if I go over 2, I'd have to be plotting a point down 1.5, which would be right there. And if you feel comfortable doing that, do it. That's great. There's nothing wrong with that point. Although I'll tell you, it's not the one I normally go for first. Because I do like the whole numbers. And anywhere I can find a whole number to plot, I do. Can you look ahead and see where we're going to get another whole number value? Let's look and see. So if I go over 3, how far up would I normally go? Yep, over 3 is normally up 1/3. What's 1/3 times 3? 1/3 times 3 is 1. And so that means that in this case, where I'm multiplying it by the 3, over 3 is actually going to be down 1. A nice, pretty whole number. And this actually also illustrates a little bit more symmetry, because you'll notice where we went over 1, down 3 to get to that point. We just went over 3 and down 1 to get to that point. Yes, there is that symmetry in this as well, so you can use that to your advantage. And of course, give me any others on either side. It's your choice about which 2 points you choose to do on either side of that first point. These were the ones I happen to choose. You don't have to choose the same ones, but notice I do say, give me at least 2 on each side. So a grand total of 5 points there. Because by giving me 5 points there, you really improve your aim, especially when we start stretching it by bigger and bigger numbers like these. All right, if I just did those points, remember, of course, I still need to be able to say what's going on up here. So, how do I get those? Well, again, you can calculate every single one based on where do I normally put the point. Or, I can just say, well, if this point is right 1, down 3, I know I'm going to have a point that is also going to be left 1, up 3. And so I could plot a point that way. I could actually go just from these points that I plotted down here and just switch them around. And if you do that, that gets you your first point, and then at least a couple others. And once you plotted those points, of course, then you have a good enough idea about what the graph is looking like. You can go ahead and draw your curve through it. And then you're done with that graph. That's what we're looking for here. And so at this point, we now see that we can graph one of these reciprocal functions with every single transformation in them all at once. You're just seeing, though, that sometimes they'll be written with the number that is the vertical shift first, and sometimes you'll see that with it written second. You will see it both ways. It's just a matter of making sure that you're aware about what it's doing, and it really is the same thing either way.